We can start? Okay. All right, good. Okay, so I hope we can start this, although I don't see it in the YouTube link yet. All right, good. So, we can start. Welcome. All right, good. Welcome to all of you to this session, which is the last live session. Which is, we had 2 sessions earlier, and we hope you enjoyed it. And also, I hope you enjoyed the course as such, which is going to end soon. So now, before I take questions from you, let me just briefly go through some of the things which kind of not covered in the course, because the course was not meant to cover this, and but it is a good thing to know. So that I'll spend a few minutes, or maybe something like 15 minutes or so on that, or a little more than that. Then if there are questions, then we can look at that. Okay, good. So this course dealt with the nuclear and particle physics, which means that we looked at the properties of the nucleus of the atoms and studied various different dynamics of that, the structure of that and the dynamics of that, some kind of models description or model that agrees, or that can actually give rise to whatever observed properties of the nuclei. That was one part of this. Then we went down to the subnuclear particles, and which are protons and neutrons, and then went down even to look at what makes these protons and neutrons, which we know now are called the quarks. And we kind of discussed briefly what is the status of the elementary particle physics in a basic way presently. Okay, so as per our understanding today, we believe that particles are, or everything around us, are made of a handful of these elementary particles. No matter whether we are talking about us, talking about things around us, or extraterrestrial things like sun or other planets, or even going beyond the solar system, and then anything that we have seen in the universe, anything that you take is made of these particles, and their dynamics is dictated by not too many different rules or interactions, but just a few fundamental forces, like the gravitational force, the nuclear forces, 2 nuclear forces, and electromagnetic force. This is what we know. And we studied some properties of these, and then classifications of the quarks, etc., and other things related to this. Now, there was a question before I actually go into the discussion of things where there is impact of the standard, the elementary particles. One of the places that we have. Before I go into that, let me address one of the questions that one of you had asked earlier. I discussed at that time. I told you that we are not equipped with many things to discuss that. Briefly, in a way, now we can actually look at that question. So the question was on the muon G minus 2. Okay, I'll just explain it so that those who are not familiar with it can understand it. This is not really, it's a little beyond whatever we could cover in the course, but there is a specific question. That's why we are actually looking at it. So, any charged particle interacts with photon or electromagnetic radiation, electromagnetic field. So, in quantum physics, in quantum mechanics, we consider the photons as the fundamental particle corresponding to the electromagnetic interaction. So when we talk about the charged particle like the muon or electron interacting with this, and we can think about it as electromagnetic, the muon interacting with a photon. So, and there is this well understood quantum electrodynamics, which tells us what are the different things, aspects of this dynamics, how they interact, what is the strength of this interaction, etc. So, unlike in the case of classical particles, classical charged particle, these muons and electrons have spin. Spin is specifically quantum property. There is no way that we can actually talk about spin like this, the spin as a fundamental property of elementary particle, like spin half nature of the electron or fermionic nature of the electron, etc. That we cannot talk about it classically. So it's a quantum property. So when we discuss the quantum mechanics of or quantum nature of these interactions, we have not only the Coulomb interaction, but also the magnetic dipole interaction. The magnetic dipole interaction arises because of the spin of the fundamental particle. And we can actually calculate how much it would be for a particle like electron or muon. And typically it is expressed in this fashion. Mu, which is a vector quantity, dipole moment is a vector quantity, that is equal to some G, which is some factor, and then mu B by H cross. H cross is the reduced Planck constant, mu B is the Bohr magneton, and S is the spin of the particle that we are considering here. For muon, it is H cross by 2 in magnitude and direction, whatever direction it has. And then what is GE, that factor that comes there? That factor is equal to 2 for a spin half particle like electron or muon, if it doesn't have any structure. So let me explain that part again. Like if you consider the proton and electron, proton has a spin half, electron also has spin half, but the difference between proton and electron, apart from being different charges, or let us take positron and the proton, both have spin half, but proton is not an elementary particle. It has structures. It is made of quarks, whereas electron and positron and muon, they are made of they are not really made, they don't have any structures. They are considered to be point particle, elementary particles. So such particles, let's call them Dirac particles, as conventionally they are called, because it arises, such dynamics is dictated by the Dirac equation, etc. So therefore, such particles, we can actually show that theoretically, the GE is equal to 2. Okay, so this G factor, that is called a G factor. The G factor for electron or muon is equal to 2. I should have written it to mu, but G mu is equal to 2 as well. Okay. So here again, it is G mu. G. So now, what is the issue? If it is 2. So it is 2. So then we can ask the question like, what is the experimental value? So before going to the experimental value, the story does not end with the figure on the top in quantum mechanics. especially in quantum field theory. In quantum field theory, like quantum electrodynamics, particles can be created and annihilated. I don't know how much of this we discussed in the course per se, but basically we can actually, I think we discussed various things. So there will be, the particles can be created and annihilated. Like when we discussed some of the interactions, reactions, C plus E minus equal to mu plus mu minus, etc. Or even beta decay. In the beta decay, we do produce electrons, whereas there was no electron in the beginning. So that is all possible only, I mean, in the mechanism, in the mathematical formalism of quantum field theory. Okay, not in the ordinary quantum mechanics. So, and one of the consequences of this is that this top diagram above the slide, or just on the top side of the slide, is only one part of the story. There could be quantum corrections. There could be additions to this. There are other things that can happen there to contribute to this GE. Okay, so this one typical possibility is what I have drawn in the diagram below that. So there we can have actually an exchange of another particle. It could be a W, or it could be a Higgs boson, or whatever, something that can actually happen, and which means that the G mu, although we are talking about the Dirac-like point particle without any structure, quantum corrections can happen to this interaction. So it's not for the particle, but the interaction is modified because of the quantum electrodynamics. So then that will add to corrections to this. So it is not strictly equal to 2 in the case of Dirac particles, but according to quantum electrodynamics, rather it will be slightly modified. And we can calculate this very precisely now. In fact, it's precise. It is calculated to 3, so up to 11 decimal places correctly. So we can see that in the standard model, the prediction is now 2.00233183620, and then you can see 2 digits in the bracket, 86. So this 86 is an uncertain one. There is an uncertainty for calculating when you calculate anything, or when you experimentally measure anything also. So in this particular case, this uncertainty is in the last 2 digits that is displayed here, that is 86. Even up to 620, there is no uncertainty. Okay, so we know those digits as the correct digits up to that. And what about the experimental value? The experimental value today, global average, what they call it, because there are 2, 3, many different experiments that actually measure this. So basically, you will actually also look at what's the. Oh, sorry, am I? I think I'm not sharing this so far. Okay, I hope it is shared now. So experimentally, so just I'm sorry that it was not shared earlier. So you can go through these things, and then the story is that when you consider the experimental and theoretical values, you see that there is a small difference. So this difference is not huge. So it agrees up to 7 decimal places, but then it varies, it differs in the rest of it, in the next 7, 8, 9, 10, 11 digits. And you can these are experimental uncertainty. These are not experimental uncertainty or theoretical uncertainty, because, as I said, theoretical uncertainty and experimental uncertainty are in the 12th and 13th digits. Okay, so you can see that clearly. There is discrepancy. There is a difference between the standard model calculation and experimental value. Now, this discrepancy is known as G minus 2 anomaly. G minus 2 anomaly. And experimentally, we have been continuing measuring this for the past more than 5 years, about 10 years or so. This discrepancy is still there. So, what do we learn from this? We can actually think about it as like there could be some slight modifications that is required for the standard model. That is one possibility. Okay, well, there are possibilities like in this corrections, quantum corrections, there could be exchange of new particles which are not there in the standard model. Say that could add corrections to this either way, and then that could explain it. So there are many theoretical proposals to take care of this, which would actually give you experimental values, experimentally compatible values. So this is basically the story of this thing. This is certainly one of the points that clearly, that possibly indicates that standard model need to be actually corrected at this level itself. Okay. So I think I will. So this was the short answer to this question that was raised. What I would do, since it is a session which is where you cannot ask questions directly, you can put it in the chat, or you can actually send me an email. Anybody who wants to know more about it can send me an email. I will be happy to explain it. So let's go on with this one. So one of the places where the standard model interaction or the elementary particle interaction is very, very important is actually the beginning of the universe. So as per the present cosmological model, the universe actually began in a state where it was a highly dense and hot state, and then as it cooled, expanded and cooled, what happened is that new particles could be created, or the particles could be created. So in the beginning, obviously, particles were created like elementary particles. It's like the electron, muon, and top quark, all the quarks and things like that, or neutrinos. So such elementary particles were created, and again, they were very highly energetic, and then moving around with large kinetic energy, and therefore we can't think about bound states like protons or other baryons. Forget about even the nucleus or atom. Even the protons and other baryons could not really be formed in the. I mean, when the temperature or the kinetic energy is very, very large. So it's a kind of a soup of quarks and gluons and electrons and other things. So it's called the quark gluon plasma. And then as it cooled down further, what happened is that the kinetic energy is smaller for quarks, say, and then they can interact more slowly, and they can spend more time with each other, the quarks, and then they could form bound states. So these bound states are like hadrons, protons, neutrons, etc. And then protons and neutrons can actually form combine together. Protons can combine together to form deuteron, and then other things, okay, other nuclei. So this is how we believe things have evolved, and then eventually, as it cooled down further, then neutral atoms were formed, where the electron and the nuclei became bound states, and then that's basically the atom, and then these atoms again form eventually the structures that we see around us. This is the very, very brief and crude way of seeing this evolution of the universe. And now there are a lot of things that we know about it, and the standard model and the nuclear physics has to actually feed in a lot of things there to understand the early evolution of the early evolution of the cosmos. So, are we all okay with it? We are okay to a large extent, but there are some bit of problems as well. In fact, there are some real problems, meaning some hard problems as well with this. One of the things, or one or two of the such things, I will tell you. Okay. This is kind of a brief sketch of the evolution of the history of the universe, temporal history of the universe in a sense. So we can actually think about it as a very small but highly dense and then highly dense and hot state. And then, as I said, particles were created, and then it was formed the structure, bound states, and then it's atoms, and eventually the structures that we see. So, in this, different epochs of the universe are kind of defined. So, the electroweak epoch, which we can understand clearly, is the one where all these elementary particles, the electron and the interactions of nuclear interactions, etc., dictating these particles, that is relevant in this stage. And that is the stage that we are currently terrestrially experimenting, for example, with the Large Hadron Collider. So that is the thing, that is the dynamics of this electroweak epoch is what basically we have been discussing in the course as well. Okay, and so it's then partly okay. So then, as it cooled down, hadrons, protons, and neutrons were formed. The formation of hadrons and protons from quarks is further hard to understand. There are ways that people are trying to understand it. No, it's still there are things that we need to understand to mathematically clearly. There are no real clear theoretical model. We have various different ways to approach this. For example, there is something, if you have heard about lattice QCD, that actually talks about the formation of the hadrons, or formation of the hadrons from quarks, one way. But as we go further down, this interaction of the protons and neutrons to become nuclei, the nuclear dynamics is rather well understood. So that actually is a very important stage of the universe, or in the evolution of the universe. So in this, light nuclei up to lithium were formed. The higher elements could not be formed. That again is explained by the nuclear physics. Like there is large band gap between the lithium and the next nucleus, and you cannot actually form the higher this thing. So that's why the heavier elements were not formed in the Big Bang nucleosynthesis. So BBN stands for Big Bang nucleosynthesis here. So this is something which you would also read from the first 3 minutes, because this is kind of the light nuclei. This epoch of BBN ended in the first 3 minutes of the expansion of the age of the universe. First 3 minutes is a book by Steven Weinberg, and that really talks about this. There are various other books, but this is a book which is written for students and then kind of people who are not working in this field. But then between that and the formation of the atom, we had to wait a long time. You can see this, that it is something like 4 times 10 power 5 years. That is 380,000 years that we had to wait for the formation of the atoms. Okay, in the first 3 minutes, nuclei were formed, but atoms were formed. The universe had to cool down and then become this atom at about 4,000 or 3,800, sorry, 380,000 years around that time. So now that's when the atoms were formed. So this is another important epoch because you can, there was also the photons in this. There are a lot of radiation in the early universe. And these photons were constantly interacting with the charged particles, like if it was a nucleus and electrons or an electromagnetic plasma like that, then this photon will interact very strongly with that. And but when you actually look at the atoms are neutral, so their interaction with photon is very favorable. It's almost negligible. So you can actually say that if you have a gas of neutral atoms and then shine it through the photons or electromagnetic radiation, then it will just pass through that most of it, except for some absorption of certain wavelengths which are allowed by the atomic physics. So now that means that all these photons which were there in the early universe were actually just free streaming after that time. So this free streaming photons or radiation is basically what we call cosmic microwave background radiation. Microwave because it's in the wavelength of the microwave presently, and cosmic because it is the origin of is from the early times of the universe, and background radiation because it is basically the radiation that is in the background of everything that happens in the universe otherwise. Like when you look at the sun, when you look at the stars, when you look at the galaxies, you see light coming from that. You can also see X-rays and gamma rays coming, radio waves, everything coming from that. Very different wavelengths of the electromagnetic radiation. But these are specific point radiation, radiation coming from specific sources. This cosmic microwave background radiation is something which is there in the background of all of this. It's like you have bulbs, small bulbs on some kind of a screen, and the screen itself is lit, and the lighting of the screen is basically this background radiation. Okay, and the spotlights are the other specific sources like galaxies and stars. Okay, and what does that tell us? It tells us a lot of things. And then first of all, okay, before coming to that, let us see. So this means that so far whatever I said, it looks like we know a lot of things. Of course, we know a lot of things, and it also looks like we can actually build things from the beginning and then goes on. It's also true that we believe that the early time cosmology can be actually dictated by is dictated by the standard model or elementary particle dynamics, and then things evolved from there to form the structures. That's all fine. And now we can ask the question: is this quantitatively measured things like how much of the electron or proton or things like that should have been there to form the structures, or how many such a nuclei should have been there, or deuteron or helium atom or helium nucleus or hydrogen nucleus or things like that should be there to actually form the structures that we see now? Yeah, and is there anything else that we can learn from this, etc.? Okay, so when you come to that, there are, and then ask the question: is standard model very well explaining everything? Then the standard model is a good description of the dynamics at the level that we have been exploring at the level at LHC, at the energy levels at which the Large Hadron Collider is exploring. Okay. Now, this there are other things like there are other issues. There are things that we don't know yet. One is called dark matter. I will explain it a little bit more details in the next few slides. And then there is something called baryon asymmetry and the Higgs mass, stability of the vacuum, neutrino mass itself. Okay, so let me not go. So there are some small problems with the standard model, small and big problems with the standard model. So today I will only, because we have a very short time, let me explain only the dark matter. Okay, out of this thing. So I said about this formation of the atom and the cosmic microwave background radiation. So it happened around this time, that for 100,000 years, or in the evolution of the universe. And what happened is that you can see that before this, these photons were actually interacting with the plasma. So any dynamics or any interaction dynamics that we have there should leave some signature in the microwave background radiation. So, and incidentally, the microwave background radiation itself was very accidentally discovered in '64, and Nobel Prize was given to Penzias and Robert Wilson for this thing. You can look at the story in detail in the internet. And then further on, there were specific missions to study, the space missions to study the cosmic microwave background radiations. And then we know now that it agrees more or less with, very, quite precisely with the black body radiation of a black body of temperature 2.78 Kelvin. And then it was independently confirmed by other experiments. In the last, there were three such missions, space missions. So the last one is called the Planck. The Planck mission actually showed us that it is all okay. And in fact, earlier even Kobe showed us that there are some anisotropies. It is expected that this, if it is coming from such early universes, because the early universe was isotropic and then homogeneous, we expect that it should be radiation should also be isotropic and homogeneous. It is isotropic and homogeneous by and large, more or less, but locally there are some discrepancies. These small discrepancies are called the anisotropies of the CMPR. So without, I mean, this such anisotropies should have come in our story because of some small perturbations or anything that would have happened in the plasma before the radiation came out, in the sense that before the atoms were formed. And that eventually would have perhaps um, uh, caused the seeded the structure formation in the universe. So that is the kind of approach that we make in the astrophysical studies. But for us, more interesting thing is to understand or the properties of the CMBR itself, and then say what we can read out from that. So without going into the details of this, forget about whatever the technical details that you have here. You can look at it later uh, at your leisure, and then ask me questions in an email or something like that. But the bottom story is that what we have in the top right corner. Okay, so it says that we have whatever the matter that we have been observing in terms of galaxies and galactic structures, everything around us. Okay, in through the electromagnetic radiations, is only 5% of the total energy density of the universe. 27% of it is matter which we don't see. So this is something which we have been trying to understand for some decades now. So then there is also the 68% of this total energy is called the dark energy. That's even more alien to the elementary particle physics. So coming to or focusing on the dark matter, which is the 27% of the total energy of the universe, we can actually ask the question, how does the standard model or elementary particle physics address this? Now, this is not the only time that we have encountered an observation which indicated dark matter. Here we have precisely computed, or we can actually quantitatively estimate the amount of dark matter, but there were already indications much before this. For example, some of you may have heard about the galactic rotation, or the rotational velocity, speed of the stars in the galaxies, especially those in the periphery of the galaxy. And that actually, the observations do not agree with whatever we think is the story that we see from the, or whatever matter of the galaxy, whatever the mass of the galaxy that we reconstruct from observations. So the looking at the stars, in the galaxy, we can actually look at, reconstruct the profile, mass profile of the matter profile of the galaxy, and it's usually that denser towards the center, and then it gradually decreases, and then eventually it becomes zero. So in that case, at the periphery, there is not really much matter. The gravitational interaction of the stars at the periphery will be dictated by if you draw a circle with the center of the galaxy and the star of the radius, we can actually see that the velocity of the stars in the periphery should actually be falling down as 1 over r. Okay, let me here. So it should be falling down as 1 over root r. Whereas it is seen to be not falling down, rather it is more or less constant or slightly growing. So the solution was to actually say that there is some matter which is not really there in the luminous matter, but rather something which we don't see. So this was one of the explanations, and then that was the time time when it was coined as the dark matter. So such dark matter, something is there, gravitating matter, which we don't see otherwise. And now we also have evidence for that in various other places, and in the CMBR also, as I mentioned, discussed a little earlier. Okay, so now there are other evidences of this, like gravitational lensing, Einstein ring, etc. Okay, so now what about the particle physics? How does the particle physics address this? In the particle physics, we have to definitely go beyond the standard model, because in the standard model we don't really have a candidate. What do we mean by that? But any particle such that which would fit in as dark matter should not have electromagnetic interaction, should be massive and weakly interacting. This is the kind of picture that, the properties that we know. Okay, the neutrinos in the standard model would have been a good candidate, but there's a problem. Problem is that they are too light, their mass is too small to actually form structures like this one. So now, so therefore, if you want to explain dark matter as an elementary particle, or from the point of view of elementary particle physics, then we need to actually add new particles to it. It could be a spin zero particle, scalar particle, or spin half fermionic particle, or it could be vector particles, or anything. Spin is not really, you can form your own theories with that. That's what people have been trying to do. So people have been actually trying to do this. Then people have been trying to find the ways to detect this. You can kind of detect it in the terrestrial experiments, trying to detect it in the terrestrial experiment. So, for example, if our galaxy has this dark matter, then we are passing through that. And if you take some heavy nuclei, that can actually, this dark matter can bombard on this heavy nuclei, and then recoil of that can be actually measured, or impact of the recoil of this can be actually measured in a way, and that will actually give you some you would be able to detect if there is a particle. Since we don't detect that, basically we will actually say that we don't see anything. Anyway, this may not be very much of interest to some of you, but anybody, I mean, this is what we say, that if the particle of such mass is there, it would have been seen, and we don't see it, therefore its mass should be larger than this, etc. So that kind of statement we can make. So if you have not understood this slide and then not understood what I told you, don't worry about it, just forget about it. Whenever you think you need to understand it, you can ask me, okay, later. All right, so there are a lot of things that we still have to do and still have to understand. Even at LSC, we have been actually trying to look for this. We are not seeing it yet. And so that's the kind of situation that we are currently in. Okay, so there's a lot of exciting things. In fact, this is only one of the things that I told you about in the case of the particle physics dynamics, which is one of the current research is focusing on. One of the areas that the current research in particle physics is focusing on is dark matter. There are various other things like the neutrinos, understanding it very well. What is how masses of the neutrino is generated, and baryon asymmetry, and then other things like that. So I believe with the small introduction of the particle dynamics that we've had in the course, you would be able to go further as you grow and then take up other courses and then go ahead in your career. And I wish you all the best. And also, if you have any questions, academic questions related to this or something that is relevant in this direction, you can actually send me an email. Okay. All right. Thank you. So let me see if there are any specific questions which I can answer. Okay. Most of you are interested in knowing how to prepare for various exams. I'm not, unfortunately, an expert in that. So I think you have to seek help elsewhere. Black hole and cosmology. Well, I did not say anything about the black hole. But so because that does not really come under particle physics dynamics, okay? So I don't think I will discuss that today. But there are a lot of interesting things in there. You would be able to learn about it at some other place. Okay, since I don't see any other questions, maybe we can stop here. And I wish you all the best again. And whenever you have some questions that you think you can ask me, just don't hesitate to send me a mail. Okay? All right, all the best.